All right, so today we're going to be talking about those sets and set operations. As I mentioned, this is something that actually is very a simple chapter, and because most of the things we've seen them before. And let me just start about this. So mainly we're going to be talking about some kind of notations and how we represent things, how we represent sets. These some kind of ways how to represent those graphically those sets. We will talk about subsets, the size of a set, power sets, which is some kind of a special sets, and Cartesian product, which is something very important to understand because especially for database we'll use that a lot in queries. So this is something very interesting to know. And then using set notations with quantifiers to represent sets. So that's pretty much what we're going to be doing this first part of the lecture. And then the second part is going to be about the set operations, how to do. We'll talk about some operations, what type of operations, the union, the intersection, the difference, the complement, the set identities, and multi-sets and things. We'll talk about more. So it's more like big words to talk about. I mean, to mention some very easy things. However, I need your attention as soon as I'm talking about something not clear. Just go ahead and yeah, ask a question. So let's talk about it. What is a set? Now, sets are group of objects that are put together. So this is the it's something that we put together this in a group. So that's mainly what is this set. So it can be most likely that these have some kind of similar properties, but maybe it's not always the case. Now let me give you maybe some examples of sets that maybe they have some things that are related together. This is a set called V for all the vowels in the English. So this is some kind of set. So these are a group of letters, but they have some attributes in common, that they have this A, E, I, O, and U. These are all vowels in the English alphabet. And we can also have, this is another type of set. We represent it with these curly braces, and each element is separated by a comma. The first element, comma, second element, comma, third element, etc. And this is how we represent those in sets. And we say now, see, all these, they have some kind of property that they share, but it doesn't have to be the case. Like I can have a set which is like this. Now what kind of property do they share in common? Well, not really. There's nothing really in common, but this is still a set because it has elements. At this time it has 4 elements. This is the first one, the second one, the third one, and then the fourth one. So these are the 4 elements of the set. So a group of things that are grouped together, or put together. So sometimes they might have some things in common, and sometimes, but not always, they might not have anything in common. They might not have any similar properties. And then let's talk about how we represent elements that are members or part of the set. Is that we represent it with this symbol, small e, which basically what it says is that A is an element of the set A. So this is just the translation of that A is an element of the set A. That's pretty much it, nothing more. And if I would like to say that A is not an element, this is how I represent it, with this E, and then I just cross it. So that's the representation that I'm saying that A is not an element of A. For example, if I go back to those examples that I said, for example, I can say that B is not, B is not an element of V. And I can say that A is an element of V. So that's basically it. And when we have many elements that I cannot just list them all together, I can use these three dots to express, as you mentioned, as you know, this 1, 2, 3, and then 4, 5, 6, or whatever, until I reach 99. So basically, there's nothing really complicated about it. A set is a group of elements that I put them together. And then this is another way how to build a set by having some kind of property. We can just represent these set builders notation. Like I have a set of x's where this is mean where x has some kind of property. For example, x is bigger than 10. So this is the set of all x's where x is bigger than 10, and I can also make it bigger than, lesser than, something like that. Or making them all odd integers. So for example, O is the set of all x's where each x is an odd positive integer less than 10. So that's the representation of the set. Now there are some kind of specific or predefined sets, like this one, which has a specific meaning. Also that one, like this Q. Actually, this is not the actual representation. If you might see, actually, this kind of has some kind of double bar for the Z, or for the Q, it has some kind of another bar for the Q. There's also R for the real number. I'm just going to actually talk about them. We have also N for the natural numbers. So I think there's, yeah, here. So here, for example, this is the N, the natural numbers. What are the natural numbers? Well, the numbers from 0 to infinite, positive, from 0 to the positive infinite. And this is, I mean, don't look at this as a minus. It's actually from 2. This is what it means. And then this Z is the representation. Actually, this is how you might see it most of the time. It's just, it was hard to find the chart. That's why the character is represented this way. So it's a set of integers. So it can be negative or positive or 0. Now if I say the Z plus, that means it's all the integers that are strictly positive. This is what it means. That means from 1 onwards. This is the integer, the positive integers. And similarly, I can have the negative integers, and that's the representation how this is represented. Q, or like as I mentioned, I think it's like this. I don't remember if it's like this, or I think it's either like this or like that. I don't remember where the bar is. Honestly, I forgot about it. But I think it's, if I have to guess, it's like this. It's on the left side. And it's the set of P divided by Q. And so these are the rational numbers, where P is an integer and Q is an integer. And also Q is not equal to 0, because we don't want to divide by 0. So this is a set of all rational numbers. Of course, when we say this P and Q, P divided by Q, these they don't have any common factor, basically. So for example, it's not like 4 divided by 2, right? Because this 4 divided by 2 is not what we mean. It's like 1 divided by 2. I mean, it could be also, it could be like included, but what we mean with this piece, and so that's, we cannot simplify that. They cannot be simplified. So 3, 2, something like that. 2 minus 5, something like this. Because we said it's Z means it can also be negative. And R is the set of real numbers, which includes basically all the rational and the integers. And the R plus is just the positive part, the positive real numbers. So these are some kind of notations that we just need to get used to. So try to remember it. We will use some of that actually. Basically all of these I'm trying to just exclude these ones, because all of them, they have this plus and then they have this minus that I can use. So I can have the n plus. Basically there's no n minus negative, so that's not possible, because it's n minus doesn't exist. But n plus is going to be what? Everything except the 0. You see, the 0 is not included in the plus. So if I say the natural, positive natural, that means I'm excluding the 0. If I say the z plus, that means I'm excluding the 0. Z minus, that means I'm removing the 0 and the positives. And the same thing with the quotients, or the rational numbers and the real numbers. Now another thing I would like to just talk about is the interval notations. So if I have like this representation, basically what it means is that if I include this, actually this is hold on. Maybe let me just copy this, control. I just would like to copy this, I can take it here. All right. So basically what is going to be the difference between these is that the equal sign. See, whenever the equal sign is there, this is going to be included. That means a is one of the values of x. That means that's what it means. If a is not one of the values of x, that means we remove this, then we represent it like this parenthesis. That means a is not one of the values of x. Hence we have now these different possibilities of an interval. If you have an interval between, let's say, 2 and 5, now am I going to include 2? Am I going to include 5? Well, it depends on how I write it. If I write it like this, 2, 5. Okay, what's going on? 2, 5, up, nice. I have to go back to here. Alright, so if I write it like this, that means the 2 is included, the 5 is included. If I write it like this, that means the 5 is not included. Another way to write that is doing it like this. You most likely seen also this, but in the book they refer to also as this way. So if you see it this way, I want you to understand that 5 is not part of the elements here. So for example, if I say like I have this set S is going to be the x's where x is greater than or equal to 2 and and less than 5. That means I'm just going to represent it this way, and this means I'm going to have 2, 3. Sorry, I forgot also to say that x is an integer. X. I'll just try to find a way to erase. Okay, I have to bring it, and knowing that x is an integer. So now I just said that x is an integer. That means it can be 2, 3, 4, and that's it. Because I said 5 is not included. So that's pretty much what it means. So if I represent with the parentheses, that means it's not part of the interval. If I use this bracket, that means it's part of it, so the equals of it. So that's pretty much what this is all about. And when we have both brackets on, which includes both limits, this is called a closed interval, and the other way around, when they're not part of it, this is called an open interval. And actually, this open interval is most likely coming from the fact that this is another way to write this. That means the A's and B's are not part of it. Right now, this is equivalent to that. So if you see this, if you see that, both of them, they mean the same thing. And you see it makes more sense with these brackets that are open, because they are kind of open. While here they are closed. When they are closed, that means it's like a box that I'm unclosing whatever is inside. Anyways, that's different ways how to see that, not a big deal. Now, if I have like this set that contains the ends, the end which are natural numbers, the z which the integers, the quotients, and the real numbers. So this set is a set that contains everything, all the possible, all the possibilities, and so Q, the set of rational R, contain 4 elements. These are the elements. I mean these type of elements, because each one of them is a type. Okay, note that the concept of data type is built in computer sets. Yeah, well, yeah. I mean, what we're talking here about the sets is actually something associated into these data types here, because a data type, when I say int x, well, basically I'm saying that x can belong to one of the sets. So that's basically what it is about. For example, the Boolean has a set of 0 and 1, or true or false, and so on. Okay, so I think let's move on from here. And okay, we're going to do some kind of another definition talking about when two sets are going to be equal. So two sets are going to be equal if they have the exact same elements. Exact same element. And this is how we write it, with the equal sign. Which means that for every x, now you remember, that means if, this means if p then q, and if q then p, or basically maybe write it much easily by doing like this here, means that we have if x is part of A, that means x is going to be part of B, and if x is an element of B, then x is going to be also an element of A. This is the B conditional that works in both ways. Remember that we said that P, if and only if Q, this is equivalent to if P then Q, and if Q then P. That's the same logic that we've seen before, right? So that's what this means. So we can say that A is a set, B is another set. They are equal only if you take every element, for all the elements, if that element is for all the x's, every number that you think of, if that x is part of A, then he's part of B. And if he's part of B, is an element of B, then he should be also an element of A. And that's how we can define that they're equal. So that's these sets are equal. So this makes us realize the order is not really that important, because these same values are here. So if I name this A and this B, I can say that A equal B, because if you take any element of A, it should be in B. If you take any element of B, it should be in A. All right. So the order does not. What did I say? Not that the order does not matter. But also that what does not matter is how many times that element is. So for example, if we have this set to be A and this set to be B, do I have like A equal B? Well, based on the definition that we just said, I take one element from A. If it's in B, that means, okay, this one is good. Take the second element. Is this one in A? Sorry, this one is in A. Is it in B? Yes, it is. What about this one? Yes, yes, same thing. And then yes, 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 it's all done. And then take all the other elements. This one is in A, yes. This was in A, yes. This was in A, yes. So I checked every single one of them. They respect the condition. So this set is equal to this one. even though you can see the number of elements actually are not exactly the same. But when we talk right now with what we are seeing is that the redundancy doesn't count. We just see if that element exists and that's it. So which means now also another example is if you have this set is equal to that set, which is also equal to this set. If you take, and you can have a lot of different combination of 1, 1, 1, 1. You can have a lot of ones, and then 2, 3. These are all exactly the same sets based on the definition of the equality, but they're equal because they have the same elements, regardless of how many are their redundancy is, how many what's the count of each one of the of those elements. So then this one is not equal to that one, just because if you look at 3 is not part of here, but every element in this one, let's see if you call that B, every element in B, so if I have X is part of B, then I know that X is part of A, because this way it works. But the other way around, if I take every X that is part of A, can I find it also part of B? Is this part of B? No, it's not, because I find one, there exists one that does not respect that rule. All right, the last thing we need to talk about, I mean, before going into some kind of different ways of how to represent these sets, is something called the empty set. Now, the empty set is denoted by this. But most likely, most of the time, this is how we're going to represent it. They call this phi, but it's like a 0 with a strike on it, a bar on it. So this means this is a null set. Same thing like we have null in a data type, or maybe the empty string, that's just like a string that we open and close. Now the empty set is a set that has nothing in it. It's also represented using this. That means this is a set that has nothing. And just this is an example of a set that has nothing. Well, an empty folder is a set, but if there's nothing in it, it has nothing. So that's actually basically what this example is trying to explain. Okay, so for example, you say often a set of elements with certain properties turns out to be null, a null set or an empty set. Null set, empty set, they are the same, okay? So the same meaning. So for example, if we have, we would like to call A a set of all positive integers that are greater than their squares. Now, I would like to have all the x's that are bigger than their x square. Can you find one? Well, it's not possible because we're talking about integers, right? So 1, 2, 3, 4, minus 1, minus 2, it's even worse, minus 3. So I would like to take all the integers that have this property where each one of them is going to be bigger than its square. So obviously it's not going to, you're not going to find anything. So this, the answer to this, that means A is an empty set, or you can represent it also this way. We also have some sets with only one element, and this is called a singleton set. This is just another definition. And a way how to confuse the singleton set is sometimes like you confuse this empty set with this, which is something we're going to talk about. This is a set. Now, notice now, it's like I'm using these two representations at the same time. That's not right, because we said either you use this phi representation or use this one, right? Now, if someone uses this and inside of it he puts this here, that has a different meaning. It means that now this set, let's call it B, this set B has one element. And what's that element? The empty set. And that's the thing. So this B has one element. So this is different from just like this. If I say that B is equal to this, that means B has no elements, which means I can also write it like B, this is equal to just a set that there's nothing inside of it. While here, obviously, there's something inside of it. So what is it? Well, it is an empty set inside of it. So that's a different thing. So just be careful about that. That's what it means. Singleton means it has one element, and these two are not equal. So that's the thing. Now, how do we represent those sets? There's this Venn diagram, which is just basically a very simple way how to represent them. We have a square representing all the possibilities. This is called U for the universe. All the possible, the universal set, which is all the possibilities, all what's possible. Among all what's possible, you just draw a circle and put things in it. Every single one of them is one element. So I have one element with A, one element with E, I, and O, and U. So these are the elements. This is one way to represent things. And this is the set V of actually, no. This is, V of vowels and all vowels from the alphabet. So here, for example, they're going to be having all the other letters like B, C, D, F. So I can have them all. So if you put all the letters in this universal set, that means all the possibilities are here. And then from all the possibilities, I just put something that is going to be, this is a set that is going to engulf some of those elements. So that's the way it's going to be represented. And we will see more about that. Let's talk now about relationships between between sets. Now we can have a set that is a subset of another set, so which means something that is part of it. So similarly, that I have like an X is an element of a set, I can have a set which is a subset of a bigger set. So for example, I can have, let's say, set B. Let me just draw like B is, I have A, B, C, D. And then this is my set B. And then I have the set A. Set A is going to be C, D. Now you see, the set A has two elements. Set B has these four elements. If by this what I mean, that means the elements of C and D, every element of here is actually part of the B. So that means now A is a subset of B if and only if every element of A, take this one, I will find it in is also an element of B. Take the other one, I will find it is another element of B. And this is how I can say that A is a subset of B. That means it's inside, like this means like this kind of representation that say this is part of it. It's like it's an element of B. When we talk about elements, we use this E, small e, and then now to distinguish between this and one element part of a set and a set part of another set is just we represent that using the something similar to E, but without the bar in the middle, and then you put it in the bottom. This is maybe one way how to remember that. We have two useful rules. Determines if a set. Okay, so now what is this about? Oh yeah, this. Well, yeah. There's some kind of rule that has been. This one, this one number 2, is very easy to prove, because what I can say is that every set S is a subset of itself. Because what's the condition for this to be true is that I need to look at every element of S. It should be in S. So obviously S is also a subset of itself, even though it doesn't make a lot of sense, but yeah, it's some part of it. Another thing is, actually, this is the one that is actually a little bit weird, is this one over here. The empty set is a subset of every set, which means if you take the empty set, well, what's inside of it? Well, there's nothing. Well, nothing is also part of all the different sets, because actually it's nothing. So this is like a rule, a theorem that you have to remember, that as long as we have a set, that set can be a subset of itself, And also, the empty set is a subset of any set that you have. So that's this other way how to, these two things you have a look at it. So what the theorem wants is that every every non-empty set S is guaranteed to have at least two subsets. The empty set and S itself. That means this one. Well, it's okay, we'll see. Maybe we're going to use that later on in some things. Okay, why is this showing up? Showing that A. Okay, yeah. Showing that A is a subset of B. Actually, to do that, we need to prove that every X that is in A belongs to B. And if we would like to prove that it's not, A is not a subset of B, we just need to find one element. We need to find if there exists one element which X is actually part of B and not part of A, and X is not part of B. So if we found just that one, we're going to prove that actually if this is true, then the A is not a subset of B. And the not a subset is, we just draw this a line that across this subset symbol. I hope all is good. Let's see, I don't know if there are no questions because no one has questions, so maybe it's because no one is raising hands. So I think I didn't do the same mistake like I did last time to disable the sound. If you write, I can hear it, just I wanted to make sure. Okay, now these are some kind of examples of the set of all odd positive numbers less than 10 is a subset of all positive integers less than 10. Right, the all positive odd integers less than 10, this is like 1, 3, 5, 7, and 9. And this is a subset of all positive integers less than 10, which is, this is the 1, 2, 3, until 9. So this here is a subset of that, which actually this makes sense. So this is just explaining, to give you some examples of that. Okay, example of subsets and not subsets. So I'm just going to move on. Now, another definition, which is this representation that actually tell us the size of a set. If I'd like to know how many elements are in that size. Obviously, this cannot be done unless S is a finite set, and that n, the value that denotes how many elements this set has, is called the cardinality of S. So the cardinality of S is the number of elements that set has, and this can be only counted for, this cardinality exists only for those sets that are finite sets, which means if I tell you the sets like all the natural numbers from 1, 2, 3 until infinite. So what's the, so if I tell you this is actually the definition of the n, right? Now what's the cardinality of n? Well, there's no way to find it because this is not a finite set. But then if I have the set A, that is the set of odd numbers less than 10, so I have 1, 3, 5, 7, 9. So then this is finite. The cardinality of that set is going to be 1, 2, 3, 4, 5, and I just count them and give them 5, which is this here. So this is how I represent how many elements this S has. So S, if S is the English alphabet, then the cardinality of S is 26. If S is actually the empty set, then how many elements this has is 0. So the cardinality of the empty set exists and it's 0. Now the set is said to be infinite if it's not finite. So basically the set of all positive integers, that's infinite, so I cannot just have one number. Now, power sets. Power sets are something interesting. Actually, it's something that can show all the different possibilities. Generally, we use them for something like combinations of possibilities. So a given set S, if we have a set S, the power set of S is the set of all possible subsets of that set S. So let's say I have a set. My S is this. Let me just maybe go back here. I'll get back to that later. So my set S is 1, 2, 3. Now what's the power set of S? This is all the possible subset of S. So first of all, remember, we said that every empty set is a subset of all the sets. And also we said that S, the set itself, is a subset of all the S. So we can say that first of all, we can have this one, and we can have the 1, 2, 3. This is an element. This is a set that is also an element of that set. It's like a big set. Let me maybe represent that in a different set of colors. It will make it maybe more clear. So this is the element. This is the empty set, and then I have the 1, 2, 3. So this is the set that is also one element into another set, the bigger one. And then I'm going to also check all the possible combination of subset that I can have, which means I can have a set of, we're having only one. This is always also a subset of S. I can also have 2 and 3. So these are the individuals. Then I can also have this 1, 2. Also 1, 3, which is another combination of sets that can be a subset of this. And is there other things? No, because the order is not important. I cannot just make 2, 1. It's the same. It's not going to be. I'm just going to repeating. I'm not going to do a start with 2, 1, etc. because it's already there. So basically, that's pretty much it. Let me just, I don't know, I'm trying to move things around. So now this is the closing of the bigger set. So that set has this empty set, the set itself, and then all possible subsets that are just having only one element, and then all possible subsets that have 2 elements. And that's the definition of this power set. So this power set of this 0, 1, 2 is going to be the empty set, the set itself, and then this 1, 0, then 1, then 2, and then the 0, 1, 0, 2, and then this 1, 2. Actually, did I miss something? I said 1, 2, 2, 3. I missed something. Yeah. I said 1, 2, 1, 3, but I forgot to do this 2, 3. Yeah, I forgot about that, right? So I caught it before you did, or maybe you caught it and then you're thinking, oh, maybe you should have corrected me. So the 2, 3 is also another part of an element of that. Is that okay? Any questions? I mean, okay question. The empty set will be always part of the power set? Yes. And unfortunately, I did not hear any notifications, so I don't know why, but I did not hear it. So yeah, from time to time, I have to go back to check, because I did not hear you writing. Normally, you should give me some kind of sound notification. Can you try raising the hand? Maybe I'm going to be able to hear the hand raise. Somebody please hear. Yeah, I hear it. So please, if you write something, raise your hand and then lower it. Then it will I can hear the notification of the hand raised, but unfortunately I did not hear the writing. All right. So yes, the empty set is always part of the power set, because it's also one of the possible subsets of the set. And then if we have a set that has an empty set in it, so what are the power set of that set? So it's the empty set and then the set itself. And because there's nothing else, that's all I have. So the power set, the smallest number of elements a power set is going to have is actually 2. And then it says if a set has n elements, the power set will have 2 to the power of n. And that's, for example, how many elements do I have here? I have 3 elements. That means I'm going to have 2 to the power of 3. And this is going to be 8, right? Which is, what happened here? 2 times 2 times 2, which is 4 times 2, which is 8. So that's why I'm going to have 8. 1, 2, 3, 4, 5, 6, 7, and 8. So these are the power sets. Now the last, but not the least, the Cartesian product. The Cartesian product, as I told you, this is a very important concept, and we talk about in database, we talk about queries. This is something you're going to be talking a lot in database, because this allows us to join information between two different sets. And actually in our case, when we talk about database, the sets are our tables. So we have different tables and we merge things together to be able to get some information that are spread out, saved into different places. The Cartesian product is going to allow us to do that. So what is the Cartesian product? First of all, it's represented like this. I represent the Cartesian product between two sets. Set A, the Cartesian product between set A and set B is going to be what? Now let's say I'm just going to take this, and then I'll go to the explanation later. To that later. Let me just take this, and let's talk about the Cartesian product of these two sets. Now, first of all, the representation is like this multiply. It looks like a multiplier, but it's an X. That means that this is the Cartesian product. When we have the Cartesian product of these two, that means we're going to take one element. First of all, this here is going to be every element of the result of this is an element that has two parts. It's actually this is denoted as an ordered pair. I represent it like this. This is not the interval like we've seen, open, close interval. No, this is an ordered pair. Like it's a pair of a group of two things to put together in a specific order, which means if I write this here like a pair of 1 and 4, it's different from 4 and 1. So these are two different things because it's ordered, so they have the order matters now. Now what I'm doing, the Cartesian product, is I'm going to take one element from A and I'm going to associate it with every single element of B, which means what I'm going to do is I'm going to have 1, 4, then 1, 5. I'm done with 1. I'm going to do now the same thing with the 2. For every element of A, I'm just going to go with 2 with 4 and 2 with 5. And this is again is going to be now 2, 4, 2, 5. And I keep going because I still have the 3. I'm going to do the same thing, 3, 4, and 3, 5. And that's pretty much it because I don't have anything else. So these are the elements, the ordered pairs that are the result of the Cartesian product from A with A and B. Now let me tell you something. How about the Cartesian product from B, A? Is it going to be the same? Well, no, obviously, because now what I'm going to do, I'm going to take the first one from here and associate to each one of the others. And because we said this is an ordered pair, the order matters. So what I'm going to have here is going to be having 4, 1, 4, 2, 4, 3, that's a with 3, and then I'm going to have 5, 1, 5, 2, and 5, 3. and that is the result of the Cartesian product between B and A. So it's clearly different from A and B. So the order from where we started is going to make a difference. There's only one case when it will not make a difference if they are the same set. If you do the A and A, for example, if you do that, then it's just going to give you the exact same thing. So that's, let's go back to the definition. So the Cartesian product is A and B sets. The Cartesian product of A and B, denoted like A x B, is, or A multiplied by B, I think it's X is more, because it's not a multiplication. A x B is the set of all ordered pairs AB, lower A, lower B, where A is an element of A, the set A, and B is an element of the set B. So this is how we represent that in terms of set notation, set builder notation. So we have, this is a set of ABs where, this denotes where A is an element of the set A and B is an element of the set B. So A, the first part is coming from the A, the second part is coming from the B. And hence this is the Cartesian product A x B, and this is actually 1 4, because we take the first one associated with 4, 1 5, and then we have 2 4, 2 5, and then 3 4 and 3 5. And note that actually this is, if I take the cardinality of this is going to be 6, which is going to be the cardinality of A multiplied by the cardinality of B, which is cardinality of B. That means how many elements do I have in A? That's 3. Multiplied by how many elements do I have in B? That's 2. That means it gives me this. Well, basically because what I did is that the combination of all these, or for each one of them, I'm just going to repeat it the number of times. So this is actually the result of that. And now if I have A Cartesian product with A, I'm just going to have A with A itself, 1 1 1 2 1 3, and then 2 1 2 2 2 3, and then 3 1 3 2 3 3, and this is going to give me 9, which is actually, and this is supposed to be square. The 2 did not go up. Let me discard this thing. Oh, this is a picture. All right. Okay. This here needs to be changed. So maybe I'll change it later. So I'm not going to waste time. All right. Cancel. This is going to take some time, so let's do that later. All right. Okay. Now, what is the Cartesian product of this? I mean, let's maybe let's take this here, and hopefully you did not see it. So, what would be the Cartesian product of this? Can you write it down on the chat? I want A Cartesian product with A and B. Well, I know that the cardinality of this is going to be the cardinality of A multiplied by the cardinality of B, which is going to be 6. So now you know that you should have 6 pairs in the result. So what are the 6 pairs? I don't want to show the writing. A1, B1, C to A to B to C. Is it 1A, 1B, 1C to A to B to C? Is that it? Everybody agrees? You don't know? Yes, no, not sure. Well, let's do that. We take the first element, 1, and then we associate it with the first element in B. That means we have 1, the pair 1A. Okay, then we keep with the first because I have to finish with all the elements of B. With the first, again, 1B, and then 1C. So this, I finished now with all the 1, and I checked all the elements of B. Now I'm just going to go to the second element of A, which is 2, and then do the same thing, 2a, 2b, and 2c. And because there's no more, this is going to be the result of the cardinality of A and B. And nobody else said anything, which means either that nobody's watching, or nobody's understanding, or nobody cares. Anyways, let's keep moving. I hope that's not the case, but yeah. So we've seen also that if the order when we do the Cartesian product is different, so these are not going to be equal. And yeah. So what if we have the Cartesian product of more than two sets? Like, for example, the general, like something like this, a Cartesian product of like sets from A1 to AN, no matter how many there are. Well, this is going to be the representation of it, which is going to be it's not going to be a pair, because I have now this like group of n tuple. That means how many n's there are. They're going to be the number of elements in that group. So there's going to be some ordered tuples, n tuples, where the first one is belonging to the first one. So AI is an element of AI for I is equal to 1, 2, 3. That means A1 belongs to the set A1, and then A2 belongs to the set A2. This is what it means. A3 is an element of the set A3, and so on, because you see we have sets A1, A2, etc., and then we have elements like the elements of the set. So AI, that means that elements from the set A1, and so on. So then if we have something like this, okay, that's not what I want. So what would be the oh no, okay, hopefully maybe I have this into the memory. Yes. All right. Now, what is the Cartesian product of A, B, and C? Now remember, we said that this is going to be A, B, C, where is the set of ordered tuples of 3 elements, the groups of 3 elements, where I'm going to have the A is an element of A, and B is an element of B, and C is an element of C. So in that regard, what is going to be the result of that? So this is going to be, I'm taking the first one with the first one with the first one. So 0, 1, 0. And then just not to get lost, I'm just going to keep 0, 1, and then get with the other one. 0, 1, and then 1. This is 0, 1, I keep them, and this is the one I'm going to change it, and keep doing the same thing. And then 0, 1, and then 2. So this is from A, this is from B, and this is from C. So it all follows that pattern. This is from the set A, from the set B, and from the set C. So just don't get confused. And now I'm done with this. So what I'm going to do, I'm going to keep the 0. The 1, I'm going to move it to the 2, and then keep the rest from everything. So this is how I can just try to not get lost. So this is going to be 0, then 2. So the A is 0. From the B is going to be the 2. And then I'll go back to the first one, second one, third one. And then 0, 2. And then 1. 0, 2. And then 2. Always remember, the first one is from A, the second one from B, and the third one from C. And then now I'm just going to, so I've did these two. I have to do again the same thing with this one. 1 with 1 with 0, and then 1 with 2 with the 0 and the others. So now I'm going to have 1 with 1 with the 0, and then 1, 1, 1, 1, 1, 2. So I finished this with the first element of B and all the elements of C. I'm going to now start again with the second element of B and all the C's. So I'm just going to say again, now it's 1, 2, and then the first element of C. And then 1, 2, 1, and 1, 2, 2. And this concludes the elements. So just to be sure, how many numbers should I have? So this coordinate of A is going to be 2, this one is 2, this one is 3. That means it's going to be 2 times 2 times 3, which I should have. This is 6, right? 6, 3 times 2, 6, times 2, 12. Do I have 12 here? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, someone did 0, 1, 0, 0, 1, 1, 0, 1, 2, 0, 2, 0, 0, 2, 1, 0, 2, 2, and then we stopped with now 1, 1, yes, 1, 1, 1, and then 1, 2, exactly. Well, you're still missing some are missing now with some others are missing though. Because you just stopped here. Somewhere on my, you stopped here. You have to still do this one. All right. So this is the Cartesian product. You're going to find this very useful once you're going to be in database, and you will remember this talk that we were having. So these are also some different examples talking about this. We have also this a square. Okay, what is that? I mean, this a square is basically the Cartesian product between a and a. Or a cube, it's a. So that's what it means. So if you see something like this, this is what it means. It's the Cartesian product of the set by itself. And see, this is with a notation, a square, to denote this a square Cartesian product with a. And more generally, this can be any n that you put. Okay. So these are just other examples. I'm not sure that I'm just don't want to spend too much time on those unless there are some questions. But I think so far it's kind of basic and it's not that complicated. Now, if we'd like to use these quantifiers in using it with the set notations. For example, if I write something like this. So what does this means? Well, this means for all element x that are part of S of P of x. Okay, what does P of x denotes? The universal quantification of P of x over all elements in the set S. In other words, I mean, what is the P of x? This is like a general. Okay. All right. Oh, sorry. So what does this mean? Is that this, which is this, is equivalent to this, which is kind of weird writing. So if they say for every element x in the set S, P of x means that if x is an element of S, then P of x is going to be some quantifications of some. I mean, this is where I need to some predicates. So some proposition. Like for example here. So this is what actually I was trying to understand what this P of x means. P of x means a proposition that is going to be this writing. So if I write something like this for every x that is part of S of P of x, that means the P of x is, I'm taking an element from that set of S and that P of x will become true. So what is P of x? Like for example here. Now imagine again, this is like all the real numbers. For every x in the set of all real numbers, x square is bigger than or equal to 0. So this, what do the statement this one mean? So this means that for every, this one means for every element, for every real number, the square of that real number is going to be positive, which a real number means it can be either positive or negative. If it's negative squared, it will become positive. If it's positive, it's obviously going to stay positive. And if it was 0, it will be equal to 0. That's why we have this 0 here. So this is going to be this, what it means. This is a true statement that says for every real number, x squared is going to be positive. And what about this one? What does this one means? This one means there is an integer where that square of that integer is going to be equal to 1. There exists an integer that its square is going to be equal to 1. Well, basically that integer, minus 1 is one of them, because minus 1 square is going to be 1. Also, 1 square is going to be 1. So we have at least 1, and this we're looking for at least 1. So we have 1. And remember, if we said the uniqueness, if I said this, that's going to be from z where x square is going to be equal to 1, then this becomes false. Because remember, this is the uniqueness. I want to only have 1 and only 1. This means at least 1. It can be 1, 2, 3, 10, but at least 1. So yeah, this is what it means. So for every real number, x, okay, so the statement is for the square of every real number is non-negative or positive. And the statement this means that there exists an integer x such that x squared equal to 1. So there is an integer whose square is equal to 1. So that's the exact same thing. So just translating these to some words. And let's have some fun a little bit with those exercises before we move on to the next part. List the members of these sets. So this means this is a set of x where x is a real number such that x squared equal to 1. So this basically we just talked about it. Minus 1 and 1. These are the possible ones, right? Oops, there's no option but to see everything. Okay, so let's do them one by one then. How about this one? X is a positive integer less than 12. That means we're going to have, are we going to start by 0? It says positive integer, so 1 is the first positive integer, and then 2, and then 3, up to 11, because it says less than 12, and it did not say less than or equal, so it should stop at 11. Okay, what about this? X is the square of an integer, and x is less than 100. X is the square of an integer, so what that means, 1 is the square of an integer. Well, 1 is 1 to square, so yes. So 1 is an answer. How about 2? Well, 2 is not a square of an integer. It has to be square root of 2 to make it 2 there, so that's not going to be it. So we said 1, and then 2, no. 3, how about 3? Well, no. 4, yes. And we have to go for that, yes. Why we didn't include 0? That's a good question. Why didn't we include 0? Because of what we said earlier, just to be consistent. Let me go back to, where was it? It was around here. So we said the natural numbers are this, right? All the integers are like this z. When we say z plus, which is all the positive integers, we said that it starts with 1, not 0. So 0 is not included in this list. So just because of this is what was considered to be a positive integer. The z plus does not include the 0. Even though, and there's, you can, mathematically speaking, 0 can also be positive and negative, but anyways, that's another discussion. But since this was the discussion, so yeah, we can have that. Well, all right, so yeah, we said 0. I did not include 0 though, because 0 is an integer. That was square of it is going to be 0. I did not include, yeah. I mean, we could also include is the square of it? No, that's it. The negatives cannot be included, but 0 is actually one of that respect that. 4, 9, and the last one is the empty set, because if x is an integer, that x square equal to, that's not possible, because the only time this x is going to be possible to be equal to the square root to be 2, that means it has to be square root of 2, and this is not an integer. So that means the answer to this is the empty set, which means there is no x that satisfies this condition. Okay, now how about this? Determine each one of them is there true. Okay, just now we can write t f for each one of them. You have 4 t or f's that you have to write, and then write for each one of them. Is this true? This false? Now if you'd like to test it, so is this true? 0 is an element of empty set. That's false, because an empty set has nothing. Okay, an empty set, is it part of an element of the set that has 0? So let's say S is a set that has 0. Is empty set part of the S? Well, you remember the theorem that we've seen is yes. That means this is actually true. Is 0 part of the 0? Yes, because, and again, S is included in S, is a subset of S, so this is going to be true. How about this one? A set that has an empty set. Is it included in a set that has an empty set? Which basically, again, it's S is a subset of S, which is also true. So it's going to be false, false, false. Oh, hold on. I said true here. And now it's false. Now which one is correct? I don't know. I did not hear anything. I don't know why. Yeah, nobody was writing, so my hearing was right. So this one is false. And I said initially that this an empty set is part of the set. Why is this false? So which one is correct? This one or my answer saying this is true? So this is a good time that is going to wake up some people. So what do you think? Empty set doesn't include, so it's false, right? So just write false or true just so I can know actually what do you think? Is it false or is it true? False. 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 All right, false. Okay, so the majority says it's false. Great. Okay, now let me ask you this. Imagine I said S is the empty set. Is that okay? S is an empty set. Now, didn't we see that if I have any, I mean, hold on, let me maybe put this, I don't think it's the right approach. Let me change my approach a little bit. I'm just going to bring, this one, yeah, this is what I'm interested in, this thing over here. So let me just do it even better. Let me copy this and then put it here. Let's go back now to the exercise. Yep, this one. And then we said, let me just press here, and we said this here, and yep, put it here. Now this thing here, see, now this here says that every set that I have, for every set that I can have, no matter what the set is, the empty set is a subset of that set. Now imagine my set now is this thing, a set that has 0 in it. Isn't the empty set a subset of S? Based on this, replace S with a set with 0 in it. Isn't this what we just said, that this is a theorem that every empty set is going to be a subset of a set S. In my mind, this is my set S. So for me, this is S. So why did we say this is false? Do you still think that this is false? Oh, let me just test you like this. Let me maybe make it a little bit more interactive. Let me get some stats. Do you still think that the right answer is false? All right, so give me your feedback. Let's see what's going on. Is think that's okay? Yes, 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 no, no. Yeah, if you say yes, yes, no, no. Or okay, so it's still many think it's yes. What about the others? Okay, wake up. I'm making the attendance. I'm checking the attendance right now. Yeah, who is here, who is not here. So you have to pick an answer. Either it's yes or no. There's no I don't know. Now again, what am I talking about? I'm talking about here. See, I'm saying that we agreed that the empty set is a subset of any set for every set S. And my set S that I'm talking about right now is the set that has 0 in it, which is this. For me, this is the set S. Now, if we said that this is a rule, why doesn't it apply to here? So, if based on this rule, this should not be false, it shouldn't be true, right? And this is the question. So you still think it's false. Actually, those that are thinking it's false are right. Why? Well, because this is false. And this is not what we're talking about. This is a set that is part of another set. This is an element part of a set. These are two different things. This is a set which is a part of another set. This is an element which is part of a set. So I'm talking about this as an element. Is it part of a set? Now, if you look at it as a set, then this is part of a set. That's right. It's a subset of any set. But is this an element? No. So that's the difference. That's why actually it's false. That's why I was wrong to make it true. And the correct answer is actually false. Right. Okay, now I hope that it's clear. If you have any doubts, you can just write about it. Okay, how about this? The A square, which is the Cartesian product between A and itself. So this is going to be what? 0. It's a pair. So let me just a pair of 0, 0, 0, 1, 0, 3, and then don't forget, I'm just going to do this. The first one with the first one, the second one, the third one, and then I'm just going to take the second one with the first one, the second one, and third one. So that means now what I need to do is 1, 0, then and then 1, 1, and then 1, 3, and then I'm going to 3 with 0, 3, 0, 3, 1, and the last one is 3, 3. And if you count how many elements do I have, I should have 9, which is 3 times 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's the correct one. And we can also do the same with this. Now this time is going to be 1, 1, 1, 2, 1A, 1B, and then 2, 1, 2, 2, 2A, 2B, A1, A2, AA, AB, and so on. So that's pretty much it. And that's the end of the introduction to the sets, and these are the basics of the sets. Let me put this down. Empty that. Do you have any questions? All good? Some people are here, but they are not here. And okay, 1, 2, 1A. All good, all good. All right. All right. Now let's just continue with this one. This is actually a little bit easier than what we've seen, because now that you have seen those, where oh no, is this the same? Where's the I want to talk about 2, 2. So not this one, the other one. Where is the other one? This 2, 2. Now we're going to talk about some set of operations between the sets, which basically some of the things that we have seen before, but we just would like to make sure that actually we all have the same understanding. So the union of two sets, if that is if I have this is a set and this is another set, they might be like this, or they might also be like they have nothing in common. So if I have something like this, that means they have some values in common, these A's and B's. But if I put them like that, that means they have no values in common. It depends. Now this is like a different type of representations. So what kind of value in common? So let's say, for example, if you have this is A, this is B. So they have in common 1, and they also have in common the 3. So this means I have 1 here, I have 3 here, and I have 5 in the A, and I have 2 in the B. So this is if I had to represent them this way. So sometimes this can be the result, and sometimes I can have, for example, a set of A, 1, 2, 3. This is A, and then the B is going to be 5 and 7 and 9 and 10, for example. So they have nothing in common. That means if I have to represent them, this is the universal set with all the possibilities. So this is A, this is B. And each one they have like these three numbers. This one has 4 numbers, and that's how it's going to be represented. But it makes more sense to represent them here like this, because sometimes we would like to also do not only the union, but also the intersection, what are the things that are in common. So the union, this is what it does. It just, all that is shaded is the result of that union. That means if I have this is A and this is B, the union of A and B is going to give me all the values of A and all the values of B. And notice that the repetition is not going to be included because we don't want to care about it. And this is how do we represent that with the U. So A, U, B, that means the union of A and B, which is all the X, if X is part of B, or X is X is an element of A, or X is an element of B. Notice the or. That means if it's in A and not in B, it's going to be part of the answer. Like for example here, this is 5. It's only in A. It's not in B, but still it's part of the answer because I'm using or. It's one of them. If it's in both, it's fine, but it's one of them. This is the inclusive or, the inclusive disjunction, not the exclusive one. Remember, the exclusive one, it's going to be either one of them, not both of them at the same time. So this is not what we're talking about. We're talking about this here, which is the inclusive or. Now the same thing on the intersection, and it's actually the U inverted. And the intersection means the elements of that intersection are going to be having A and B. So both that are in common, these are the ones that are going to be in the result of that intersection. So in this case, I have 1 and 3. This is 5 here. Sorry, and this one has 2. So this is not going to be part of it. So the answer is this 1, 3, because this is the shaded one, that the thing that has in common. And this is the intersection. I think it's all good, all easy, and no problem. Yep. The difference, maybe this is where maybe I don't know if you've, most likely you've seen this. And by the way, all these things that we're talking about, the union, the intersection, this is also something you're going to see a lot in database, because we use that a lot to have different set of values. I would like to join them together like a union, or just have the intersection, only the ones that are part in 2 places, etc. So this is also something you're going to use a lot in database. So the difference now is actually is not like with this minus. If I have this a minus b, that means I have all the a's, but I exclude everything that is in common with b. So that's what this is actually meaning. So I want all the elements in A minus remove everything that is in B. So that's what it means. Again, if they have nothing in common, there's no, okay, the result is going to be just A minus B is going to be just A. But if there's something in common, then whatever this thing is in common is not going to be part of the result of A minus B. This here. Alright, so this is again the Venn diagram representing it. It's much easier to see it than there. For example, if we have this is A and this is B. If I have A minus B, which means I'm just going to have the ones, this is part of B, so I'm not going to have it. This one is not part of B, that means it's going to have the 3. 3 is still also part of B, so 3 is not going to be here, but 5 is, so I'm just going to have the 5. And am I going to include the 2? No, because I'm saying everything that is in A and not in B. So I'm not checking all the ones that are in B and not in A. So that's going to be for another thing. If I use B minus A, then this is going to be the 2, because only 2 is not in common between them. So that's what this means. So this is the union. Again, another way how to represent things. The union, the intersection, the difference, A minus B, and then we can have like a lot of different type of things together. So A minus C. So this is actually designed just to trick you a little bit, because as you can see, A, B, and C, they have some things in common. This is between A and B. They have in common between A and B. This is what is in common between A and C. And this is in common between A, B, and C. This is now, this part here is in common between B and C. So let me maybe color this, highlight it. Can I highlight? It will be maybe better. Yeah. So this part over here is the part that is going to be between A, B, and C. But if I'm talking about A minus C, so this is C. That means what's in common are these one over here. So these are the ones that are going to be part of. These are parts of the C that I don't want. They are part of A and C, but I don't want them, because I said give me A and remove whatever it's part of C as well. So this is going to be the answer, the gray one. Now A minus B is just the same idea, except that this is just going to focus on the B. Where is it going to be? So this is actually, I mean, if I represent the whole B, this is the whole B. So I'm just going to take A and then remove anything that B has. So inside my A, I have some things that are B has, so I'm just going to remove it. How about this? Now A, and I'm going to remove from the A, I'm going to remove B, the intersection between B and C. So this is B and C, the intersection between B and C, that means this is what B and C have in common. This is what the intersection is. So that means these are the elements that are both in B and in C. And if I say A minus that means I'm going to remove from A anything that is in this yellow area. Well, in this case, as you can see, these parts over here are going to be part of it, because what I'm removing is actually only these ones that are in yellow. So again, we can play around with these operations. Now the one that maybe you have not seen a lot, which is called the complement of a set. Now the complement of a set is denoted with this bar above it, and actually this means everything other than what's in A. Anything else. Remember, we said this here is the universal set. That means all the possibilities. Now, for example, if I say that my X is actually all the where X is a natural number, let's say, that means X, a natural number. Remember, a natural number means 0, 1, 2, 3, etc. So that means this is going to be all the natural numbers. Now, if A is going to be 5, 7, 9, and okay, I'll remove this one. I don't need it. So 5, 7, and 9. That means here outside of A is all the odd numbers, so 0, 1, 2, 3, 4, and 5 is here, I'm not going to include that. 6, 7 is here, I'm not going to include it. Then 8, 9 is here, I'm not going to include it. So 10, 11, 12, 13, etc., etc., until infinite. So the complement of A is all the other values that are not in A. So it's basically other values are the universal set, and I'm removing from that universal set that A, all the values in A. So that's the shaded one. Is what it means. So for let's have some kind of maybe some examples of the complement of this. For example, let's have the A is like this vowels. So the vowels from the English alphabet. So the complement of A say all the letters in the alphabet without these ones. So that's what would be the complement. So the A is there. So B, C, D, then E is here. F, G, H, I is there, J, K, L, M, N, and then O is there, so P, etc., etc. So that's what the complement means. So you take all the possibilities, the universal set, and then you remove from it whatever is that set is. It gives you that complement. Okay, we have some set identities, which is very similar to the rules that we had with the that we've seen in the previous chapter with the propositions and the propositional logic. So if you have any set and then you do the intersection of that any set with the universal set, basically it's just doing the set itself. So the set A, so this is the universal set. And then you have a set A that is there. And then you do the intersection between this and the universal. Well, basically, it's only going to be that same A. Or the same thing, union with the empty set. The set with a group, anything from an empty set, is going to be A. So these are some sets of identities that makes a lot of sense. For example, if you do the union of A with itself, or the intersection of A with itself is going to also be the A. Or if you have the complement of the complement, which is the complement of A, and then you complement the complement. So this is going to give you back to A. So that's what it means. And you have these commutative things. If you have like A, the union of A and B is the same as the union of B and A. So that's what it means. You just swap them around. It just works the same thing. And also associativity. A, the union of B union C is the same as A union B union C. So that's what it means. You can move around the parentheses. Same thing with the intersection. And the distribution also is, if you distribute this union and intersection, so the A in the intersection, or the union, sorry, let's start for this first one. With the B intersection and C, that means you're going to distribute this A union B intersection and A union C. So basically the same thing that actually we've seen are applicable. The De Morgan's law also is applicable here. You remember the De Morgan's law is the one that if we negate like the A and B, it's going to give us negation of A or negation of B. That's what we've seen, right? So the same thing similar here. If you do the negation, but this time the negation is going to be with the complement. The complement of A intersection B is going to give you the complement of A, and then the union, the complement of B. So just change these to, if it was an intersection, it would become a union. If it was a union, it becomes an intersection. Absorption law, which basically what it says is if you have this, okay, let me just do something. So this, I don't want to go in too deep, but let's do it. So for example, the union with the intersection of A and B. So we said that we can distribute that, so that means A union A, and then we do the intersection with A union B. So the union of A and A, that's A. And the intersection between A and A union B, what is going to be in common between A and A union B? What's basically that's A. So that's why we have that. So you can also just by doing the distribution, like what we have here, and then you get to this identity. It's called the absorption law. The complement law is that if you do the union of this and its complement, that means it's all the possible numbers. And if you try to intersect this A and its complement, there's nothing in common, so it's going to be the empty set. Let me know if you have any troubles with this, because I mean these are just basic rules that can be we can test them. If you want some examples, just let me know. We can also prove that actually that these are the equivalency of membership, or maybe the membership of using the some kind of this called it not truth table but membership table, which is very similar to the truth table though. So what does this mean? So a membership tables means these are all the possible elements. If there's an element in A, and this means it's going to be by 1. So an element that is in A and that is in B and that is in C, is it going to be in the union of B and C? Well, yes. If it's in A and B and C, is it going to be part of the union? Well, yes. Between B and C. Let's have a look. Sorry, let's have a look just between B and C. Now, if I have this, there's an element in B, and then the element also exists in C. It's going to be in the inclusion of B, the union between B and C. If the element is in B but it's not in C, and we are doing the union between B and C, so it's going to be part of that union. So that's what this means. The only time it's not going to be part of it if it's that element is not in B and not in C, so obviously it's going to not be in the union of those. So this is actually very similar to these truth tables, but except that we are looking for what is going to be the result if I have an element in A and that element is also in B and also in C. How is going to be now? Can I answer this doing that? So to be able to do that, we can just, is it going to be in this answer? To be able to answer that, we just do them the same way that we do the truth tables. And if we'd like to use also these to prove that these are having actually the same elements, we're going to do again like this membership table, which is again very similar to the logic behind the truth tables. And if we can prove that they have the same memberships for all the different possibilities, that means they are equivalent, which means they're equal. They have they are the same. They contain the same elements. I'm not sure if you're still with me. All good? Hopefully. Yes. Good. Alhamdulillah. Great. So yeah. What's that? I think I went. Oh yeah. So this is just if you'd like to show something like that, this is like showing that we can use these to prove how to make the proof like this is actually equivalent to that. You're proving it by using these laws that we have seen, the set identities that we have seen before. Let's do one, for example, just for fun. Let's do one, but I don't know if there's an exercise that we can do that. Oh, there's no exercises. Or there's, I don't know, my computer is not responding. Okay, so what happened? All right, so this is 2-2, so there is something. Okay, why did it stop? Okay, actually I just noticed that we still have a lot of things to cover. I don't know if I don't want to spend too much time on this, but the idea is well, let's maybe just discuss this one. Control print. I'm just going to print this very briefly. I'm just going to copy these and put them in here, and then zoom out and check this thing. I remove that. Okay, so what we're trying to do is to prove that these two are equivalent or equal. So how are we going to do that? So we're going to use whatever we have here to, okay, why doesn't it want to, all right. Oh, so I just pasted it. Okay, and then let's just move these. All right, so starting from here, what is the, okay, starting from here, we would like to do some equivalences and identities to reach this. So the thing is, the first thing we can do is, let me just go back. So the first thing we can do is that we can just do the Morgan's law on this one, right? So if we have something like this, this is going to be equivalent to the complement of A intersection the complement of B intersection with C. This complement of the whole thing, right? I just applied this De Morgan's law when we have something like this. This is my A and this is my B. The whole thing is my B. Let's say this one, where I'm going to just use this one here. All right. So then again, I'm just going to now do the De Morgan's law again only on this part, which is going to be, this is the complement of A intersection of what's inside is going to be the complement of B union the complement of C. Somebody raised his hands or her hand, or there's something we should flip the sign between B, C? Flip? No, not yet, because what I did here, I'm going to flip it only if I'm just going to now put this complement inside. What I did here basically, I'm looking at this as if like this is A union some Z. And all I did here after doing that is A union Z, the complement of that is going to be the complement of A intersection the complement of Z. For me, Z is the whole thing. This is Z. I did not touch it, but it's just Z. Now I'm just going to touch it now. So from here, I'm just going to now look at Z, replace Z with this B intersection C, and then I'm just going to do the Morgan law again and apply it to it. So now I'm just going to this. If I look only at this, just take it separately. If I use this like that, this is going to be equivalent to what? Well, the complement of B union the complement of C, which is what I did here. Is that okay? So I did it one step at a time. I didn't want to do it all at once. Doing it all at once is going to give us maybe some issues, right? So I just want to do one step at a time, just not to get confused. We could do them all at once, but then it's not a good idea. So we might just get confused and mixed up. So this being said, now I have done this. I can now do this distribution, which is like this here. No, sorry. This is because not this one. This is associative. Oh, I'm just talking about the distribution. I'm going to use this one over here, the distributive law, to distribute the A intersection with B, and then the A intersection with C, and then this is going to be union between them. So this is going to give me A, sorry, not A, because the complement of A, the intersection with the complement of B, this is one thing, and then I have the union with the complement of A with the intersection of the complement of C. Is that okay? All I did is this over here. Sorry, this, where is it? This one over here. All good? Okay. So now I'd like to reach this step here. How can I do that? Yes. All good. All right. So how can what should I do now to reach this? So I'd like to have something that is going to take me to this thing. How can I do that? Well, in the first place, why did I have to do this? So if, I don't know, but to me, this whole step that I just did is useless, because it doesn't help me to reach what I want to reach. What do I want to do? I want to prove this. but I'm there. Isn't this, if I swap these around, I have the intersection, that's here. All I have to do is swap these around. So basically what I have to do is say, you know what? If I reach this, all I can say is, because of this commutative law, I can prove that this is going to be B, complement of B union complement of C, intersection with A, which is this thing here. I'm having this the same. The only difference is now, instead of C union B, I have B union C. But I know that this is going to be equal to that, which is going to give me actually C complement of C union complement of B intersection with A, complement of A. So it gives me that what I wanted. So I don't need to do this distribution thing because I'm there. All I have to do is just move things around. So this is how we can prove things, by just using these laws and just to prove that two things are similar. Is that okay? I hope. I got you with this distribution and you just kept going. You should have stopped me as well. So if you see me doing something that doesn't make sense, you should let me know. All right. Where are we? Yeah, let's talk about now what is left after this. What is this? Because intersection and unions and intersections are sets of sets satisfy associative law. Yeah, okay, so we talked about those. Yeah, we spoke about that. So this is all done. Okay, let's talk about well, yeah, this is another type of notation that we can use. Sometimes you might see it. It's nothing more than just to be able to understand. If you see something like this, what does it mean? This is what it means. It means it's the union of many sets. The set where I is going to be 1, then 2, then 3, then until n. So which is going to be like the set A1, a union with the set A2, because now we said I is going to be equal to 1, 2, etc. until to n. So this is what it means basically. Same thing with this is the intersection for all the sets. So the collection of sets are, yeah. All right, so that's what this represents. Okay, I don't want to spend too much time because I would like to talk about these multisets. And these multisets is the last part we're going to be talking about, and this is actually the part where, if you remember, we said that if we have something like this in the sets, we don't care about the repetition. Now in the multisets we do care now. We would like, when we talk about multisets, to make a distinction between those that have these 3 A's and 2 B's and those that has 1 A and 2 and 3 B's, for example. So these two multisets are different. These are two sets that are the same, but if I'm talking about multisets, then I pay attention to the repetitions or the recurrence or the occurrence of the numbers. And this is one way how to represent them, is that if for every these m's are going to be the number of times each one of the element is repeating. So for example, if I have something like this is going to be like 3 A's and 2 B. So this is how I can also represent this here. So this is this, using this notation with the occurring AM is occurring M1 times. So let's have a look at some examples. Now, for example, let's have a look at this. Now P is this multiset and this is Q. Now when talking about multisets, now the union, the intersection, the difference, these are going to be having some slightly adaptation that we need to do with it. So this means that I have 4 A's, 1, 2, 3, 4. I have 1 B and I have 3 C's. So this is what it means, right? So P, this is P. What about Q? Well, Q, it has 3 A's, A, and then 4 B's, B, 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 and B, and then 2 D's, D and D. That's Q. Now if I'm doing the union, now the union of this is going to be what? Again, I need to see every single element that is here and there. Now this one is here 4 times, but this one is 3 times, which means with the union, which one is going to be having. So I'm going to have every one of them that is here, regardless if it's there, right? If it's there, so if I put 3 as the result, that means they have 3 in common. Actually, there's 4. This 4th one is not going to be part of it, so actually this should also be part of it. So the idea is that when I do the union, I'm looking at the maximum between the elements that are the same. So I have A here. So I'm just going to say that the result is going to be, the union is, I'm got 4 A's. I had 3 here on that side and 4 on this side. So the maximum is going to be 4. What about the B's? I have 1 here, I have 4 there. So it's going to be the maximum again between the 1 and the 4. So it's going to be 4 B's. What about the C's? I have 3 here, I have 0 there. There's no C's. That means the maximum between 3 and 0 for the C's is going to be 3. And the same thing, the D's, there's no D's here, but there are 2 here. So that means I'm going to take 2 D's here. So that's the idea behind this union of multi-sets. Before we're talking about unions of sets. In union of sets, we don't care about the duplications. We do in multi-sets. So then how does the union work? Well, it works with, when I'm going like to group with the union, that means I'm grouping things together, I'm getting looking at the maximum. On the other hand, when I'd like to have the intersection, which means I would like to have what do they have in common. Okay, what do they have in common? Then this time, I cannot say 4. They have 4 A's in common. Now they don't have 4 A's in common. They have 3 A's in common. So I'm looking for the minimum between the 4 and 3. So what do they have in common? I have 3 A's. Do they have B's? Yeah, I have. This one has only 1. This one has 4. That means they are having in common 1 B. How many C's? Well, they have 0 C's and 0 D's. Which basically all this is what they have. So 3 A's and 1 B. That's what they have in common. This is the result of the intersection of multisets. So it's slightly different from what we were doing, and that's how these multisets work. Now it's kind of easy to understand with the union and intersection, but what about the difference? The difference is actually slightly interesting. Let's say the difference. I would like to have the difference between this P and then this Q. So that means I want all the elements in P, and I need to remove all the elements from Q. I have 4 A's in P, 3 A's in Q. I would like to remove all the 3 A's, which means I will be left off with 4 minus 3 is going to be 3 A's. That means this is going to be only 1 A that is going to be remaining. So that's why it's represented this way. I'm going to take the maximum between 4 minus 3 and 0. Okay, why the 0? We'll see it now. Let's say I'm just going to go for the B. I would like to again do P minus Q. That means I would like to exclude from P all the Q's. So how many I'm going to exclude from? I have 4 B's here, but here I have 1 B. So if I include in anything that B has, the Q has, this is P, this is Q. If I exclude everything that this has, that means I have to remove this one because from the B's. That means I'm going to have 1 minus this 4. This is going to give me minus 3. So what's the minimum between? I'm not going to look for the maximum between this minus 3 and 0, which means because it becomes negative, that's why the 0 is here, because if this one is smaller than the number that is here, I'm going to remove that number completely, and it's going to be left with 0. After removing all the B's from here, I removed all of them, and then that means I'm left with 0. And this is the result of this 1 minus B is going to give me the minus 3. The maximum between minus 3 and 0 is going to be the 0. So at the end, I'm just going to have 0 B's, which is B is not going to be part of the answer. And then what about C's? I'm going to take C's and anything, I'm removing any C's that I have from here. There's no C's to remove from here. That means it's going to be 3 minus 0 from there, the other side, so it's going to stay as 3. And what about the D's? Well, same thing with D's. I have 0 in here. I remove 0 minus 2, that gives me minus 2. and I'm going to get the maximum between the -2 and 0, which means I'm going to include any c's. I'm not going to include any d's. Sorry, I'm going to include any d's here. C's, we're going to include 3 of them because c's are here, not here. And I'm removing q. I'm removing it from p because I'm using p minus q. So that's the p minus q, what it means. And then p plus q, well, it's actually is going to be, it's not the union, notice, it's actually going to add these things together. So if I had 4 A's and 3 A's on that side, that means the total is going to be 7 A's. So that's a new operation that we're seeing. This plus here is not like a union. Union, I'm looking for the max, what they have in common. Here, I'm just adding them up. I'm adding them up, whatever they are. I'm just adding all. It's not like I'm putting everything together. The union, I'm not putting everything together. I'm just looking at what do they have in common. Sorry, what do they, I'd like to have all the elements from both sides. I said what they have in common. What they have in common is the intersection. Again, I was saying something wrong. So here they have not all what they have in common. I'm just going to get all between the both sides, what they have in common and what they don't have as well. Like for example here, because they have in common, like here they have 4 A's, 3 A's. What do they have in common is like these 3 A's. So that's what I meant initially by saying what they have in common. But then if I say what they have in common, they don't have in common C. So maybe people might think that C should not be part of the answer, but it's actually what they have in common in terms of the things that are available in both sides, and the things that are only available in one side, so it's going to be all of them. That means this 3C is only available in P, so I'm going to include it, all of it. Same thing with the do D, same thing, that's going to be all of it. But for the others that have, like there are some that have in common, so which one that I'm going to have, say it's actually looking for the maximum that I can have. So it's going to be the union of all of them. Alright, so this being said, I think that's pretty much it. Let's do some exercises just to make sure that we didn't skip anything and we didn't miss anything. Okay, let A and B describe the students in each of these sets. Okay, I think this is fairly easy. I'm just going to skip this first one. I think maybe even this, okay, let's do this one, number 2, quickly. So the union between A and B is going to be all the elements from here, from A, that means 1, 2, 3, 4, 5. And then also the elements from B, which is 0, 3, 6. Hold on. Am I going to put 3 here and 3 here? No, that's the right answer, yes. So I'm going to do the union. So 1, 2, 3, 4, 5, 6, and then 0. I should have put the 0 before to be, anyways. Right? Yeah, okay, good. What about the intersection now? For the intersection, do I have one by one or all of them? Okay. Yeah. What about the intersection? What do they have in common? There's only one that they have in common, which is the 3, exactly. Okay, if I have A minus B, that means I'm removing from A everything that is existing in B. In this case, I'm going to remove the 3 because this is what they have in common. So I'm going to remove the 3, I will end up with 1, 2, 4, and 5. What about if I remove the opposite, I remove everything from B, remove everything that is in A. That means I'm going to look at here and remove anything that they have in common, the 3 here, so it's going to be 0 and 6. Yeah, so these are also same things. I just would like to go for the multisets. Yeah, the multisets, it's just play with those multisets. Okay, what about now A union B? So what is going to be the answer for this? Remember, when I'm doing the union, I'm looking for the max of the two numbers that they have. For example, for the A I have 3, and then for the other A I have 2. That means I'm going to have, this is going to be 3 A. What about the B? The max 3B. What about the C? There's no C in here, so it's between the max and there's 0 here. That means 1C. What about here? There's nothing more. What about here? Do I have something that doesn't exist there? 4D, so it's going to be 4D. Am I right? 3A, 3B, 1C, 4D. All right, 3A, 3B, 1C, 4D looks the same. Anybody has something different? No? Right? All good? Okay, let's remove that. And 3A, 3B, 1C, 4D, that's great. So, alhamdulillah. What about the intersection? On the intersection, I'm looking for the minimum. I'm looking at this one, minimum with that one, so that means I'm going to have, you know what, let me just write it here so I can have some space to see compare them both. So 3A and 2A, that means I'm looking for the minimum, I'm going to be having 2A. 2B's and 3B, that means I'm going to have the minimum with 2B. 1C and then 0C, which is the minimum, is going to be 0C, which is not, I can just not put it. And what about the D? 0D here and 4D there, so it's going to be, again, the minimum is 0, so, oops, sorry, it should be B. So this should be the answer. The others are going to be zeros. So 2A and 2B. Good. You can put the zeros and remove them, that's the same. Okay, the nice one, A minus B. Okay, when we do the minus, what are we doing? We're taking this one minus that one, and then that means I'll have 1A. What about the B? What should I do? Remember, I have 2 B's from here. I need to remove 3 B's from the 2 B's. So how many are going to be remaining? Well, obviously, if I have 2, I remove 3 from it. It's going to be minus 1. So I'm not going to put minus 1. So everything that is actually negative, that's why actually we said it's going to be the max between the difference and 0. That means if it's negative, I'm going to keep 0. So as soon as I find the negative, it's going to become 0. So this here is going to be 0B, and later on I'm going to remove it, but I'm just going to keep it here just to be clear. And then I'll take the question just in a minute. And then C, I have 1 C, and I have how many C's there? 0. So 1 minus 0, it's going to stay with 1 C. Okay, what about the D's? I have 0 from here for the D and 4 here. So that means 0 minus 4, this is going to be minus 4. And because it's negative, I'm not going to include this, it's going to be 0D. So basically, what I'm going to have is just 1A and 1C. That is going to be the answer. I hope that I'm correct. And 1A, 1C, great. 1B, there's no minus. You should not put any minus. You cannot have a minus. It has to be 0 at the maximum. So if you find a negative number, it has to be 0. So you cannot put a negative number as a number of elements, because this represents the number of times we have C. And you cannot say I have minus 1 times C. No. It's either you have 0 or 1 or whatever. You said B, minus 1 times B, so it doesn't work. Okay, why 1A? Okay, that's a good point. Why do I have 1A? All right, so let me backtrack a little bit. So we would like to do again A minus B. So we're going to take from A the B's. So let me just represent them like this. I have A, and let's look only at the A's. And this is, I have A, two of them, sorry. Only 2 of them. So I'm removing, this is A and this is B. I'm removing from A anything that is in B. How many A's do I have in B? 2. So I need to remove 2. This is it leaves me with 1A. So that's the idea behind this minus. I'm removing from the 3 A's the 2 A's that are in the B. And that's why I have 3 minus 2 gives me just 1A that is remaining. Now here, the B's. I have 2 B's here. and I need to remove anything that is from the set B. So I have more in the set B than I have in the A. So that means if I remove all that is from the B, it's going to remove all the ones that are from the B and leave me with actually 2 minus 3. It's going to give me with minus 1. But am I going to say I have minus 1B? No. Every time this is negative, I'm going to say, oh, this is going to be 0B. There's no B left in A after I remove 3. Actually, only 2 are enough to remove all the B's. And that's the idea. Now from the C, for example, I have 1 C here. How many C's do I have here? Well, I have 0 C's, which means I'm going to remove from the 1 0 C. That means I'm just going to keep that 1 C. So it will stay as it is. And if I would like to continue, how many D's do I have in A? Well, I have 0 D's. Okay, let's remove from the 0 D's the 4 that are in here. So this is going to give you a negative number. Every time negative number we don't touch, we keep it at 0. So it was 0, it will stay at 0. So we don't touch. It's not there anymore. Is that okay? Good. Now let's do the B minus A. This one is interesting. B minus A. That means I'm going to take 2 A's and I'm going to remove from them 3 A's, which basically 2 minus 3 give me the 0. That means I'm going to have 0 A's. So A's are gone. From the B, I'm going to remove 2 B's. I have 3 here. So 3 minus 2 gives me 1 B that is going to be left. Okay, from this side, on this, how many D's do I have? I don't have C's, so I don't care about them. So I have C's. I have 4 D's here. I'm going to remove anything that is D from the A. How many do I have? Well, there's 0, which means I'm going to stay with 4 of my D's. I'm done here. That means the result should be 0A. I'm not going to write it. So 1B and then 4 D's. Do you agree with me? Yeah, 1B. Yep. And 0C. Yeah. Okay. That's right. So this is going to be the right answer, hopefully. 1B and 4D. Great. Now with the plus, it's just the addition. So I'm going to add all what I have, which means how many A's do I have? 3 here, 2 here. That means I'm going to end up with 5 A's. B's. 2 here, 3 here. That means 5 B's. And then C's. 1 here, 0 there. That means I'm going to have 1 C. And then D's. 0 here, 4 there. They're going to have 4 D's. That's the A plus B. 5, 5, 1, 4. And that's great. All good, inshallah? The best slide ever. Any questions? See, I told you this one was very easy. It's just we have some small things to pay attention to, but it's not a big of a deal. So if you don't have any questions, feel free to go, inshallah. And we're going to not meet next week because we have this national day, so we're not going to meet that week. So don't forget about everything. This time I'm not going to make the same mistake I did last time. I was just trying to bring the questions as fast as possible. I did not check the questions and it ended up having a lot of duplication, and then among that duplication the correct answer was messed up. So I really apologize for that. That's why for the quiz I just removed all the nonsense and kept only a few questions actually from the last 2 sections of chapter 1. This 1.7, 1.8, you have noticed that actually yes, you can see the mistakes from the quiz. Actually, at that time it was blocked until 11:30 because I've been asked to do that. Some students were still taking it, but now it's available. It's available for everybody. Yeah. So now, inshallah, I will prepare the pools for the questions for these sets, and I'm going to make them available for you to review. And we are going to use those, inshallah, for when we come back after the next week, because next week there's no classes. So on Tuesday, just to be clear, there are no classes on Tuesday. So we will have the mini test as planned. And yeah, let me bring this. See, but we didn't have a mini test here today because you had the quiz. That would be enough. We're going to have mini test 3. This mini test 3 is going to be about the sets and set operations. And then we're going to be talking about functions, inshallah, for our next meeting we are going to meet. Any questions? Doctor, I sent you an email about some. Yeah, I didn't have time to check some emails. I've seen that I received some emails. I did not check them. Inshallah, I will check them later. I will answer that. I saw the emails, but I did not see I did not read them actually. If you have any question you not understand, whatever, something's not clear in the quiz, just send me a screenshot. When you send me a screenshot, it makes it even easier for me to understand exactly the problem, which question you're referring to. And yeah, if you're not sending me emails from your official email, from the college email, then make sure that you mention your full name and your ID, so I know exactly who to find, so I can check on Blackboard your submission, and then I can understand much better what happened. There are no mini tests today. Yes, the only question was that no question that I asked, but that's it. There are no mini tests for today. And again, I strongly advise you to go back to the plan. We're going to follow the plan as closely as possible. So far we're doing good, because we did the mini test 1 on week 2, mini test 2 on week 3, the quiz 1 on week 4, and there's nothing on this week, next week, and there's also only the quiz 1. So mini test is going to be also then week 6, inshallah, after the week after next week, inshallah. So have a look at this. Don't forget about it. There's a mistake I saw based on it in the quiz. Just send me a screenshot. Okay, send me a screenshot. Explain to me what's going on in the screenshot, and then I'll be replying you by email, inshallah. Any other questions? Again, if you don't have any questions, you're free to go. See you, inshallah, after next week. Can we see our mistakes? Yes, you can. Just go to Blackboard. You'll be able to see them now. I mean, since the morning, but yeah, now you can see them. So check your mistakes. If something is not clear, just send me an email with the screenshots. So it will be much easier for me to understand the problem or the question. Yes, go ahead.
Doctor, how long is going to be the ability of seeing the mistakes in the quiz?
It will be available until we close the semester, inshallah. Any other questions?
Doctor.
Yep.
About quiz 2.
Inshallah.
Is it possible if you make the time for the quiz longer؟ لأن الصراحة بالكويز اليوم أعتقد إنه مو بس كلام، حتى كلام الطالبات إنه يعني الوقت كان شوي ضيق بالنسبة للأسئلة.
Look, I understand the timing, but the setting is also actually, I think I was giving you a gift, because all the type of questions I'm allowing you actually to let me go back here. See, the pools of questions are the same that you have here, and you're allowed to do the exercises multiple times, this review test multiple times, and by seeing multiple times you're going to be able to see almost, if not all, the questions. So you'll have an exposure to all the questions. Now, if you want me to give you more time, I will not give you the questions from like what I did right now. I'm just going to have a special set of questions that are not going to be the ones that you have seen before in here, and then I'll make them the quiz. I give you more time. But I think it's not in your advantage. Allahu alam. Based on what I saw, even the statistics of the when I checked the submissions, very few actually continued up to the 30 minutes. Many finished actually. Let me be more specific. About, let's say, 40%. They finished around 15 minutes or less. And then we have maybe another 20 to 30%. They finished within like 25 minutes, and very few actually remained until the full 30 minutes. Which actually, that makes sense to me. It's logical to me, because if you review all these tests, these mini test reviews, it's basically the same set of questions. I did not exclude some questions that you're going to see them for the first time during the quiz 1. All the questions that you saw in the quiz 1, you would have seen them in those mini tests. So it's kind of unfair to actually make it too easy because this is going to not encourage people to practice a lot. So if you practice review
Okay,
a
but
lot, it will
can
help
you
you to
make
get a good
the
grade.
questions
I'm sorry?
less? Can you make the questions less?
Well,
Same
again,
time,
it's,
but
that's
not
the same thing.
40, make it
So it's
35,
it's
30.
the same discussion. The time is based on the questions and how many questions. So if you just change the number of time or questions or change the time, that's the same result. You're not getting my point. My point is I'm making it easy already. Okay, let me do something. Make a decision. I have two options for you. I want the whole section to decide, all sections to decide. If you want more time or less questions, I'm going to give you the quiz from questions you have not seen before. Or I keep the same pattern. I give you questions from like reviews, and these are the reviews. I'm going to give you questions from the quiz too, from those questions that you have seen. Now you decide. You have a week of thinking. If you have a WhatsApp group or whatever group, you can have the discussion there. Take a vote, and then the week after we come back, and then the first week when we meet, inshallah, that means in 2 weeks, you tell me, okay, we all agree to do this, and then I can go from there. But I think it's not in your favor to do that. But anyways, I'm leaving the door open. Anything else?
Doctor, we can leave?
Yes. If you don't have any questions, you're free to go.